Hi everyone, this is Jake Fry again, and today I'm going to talk about derivatives. So we're still describing motion, but in order to best understand how to describe it, it is much better to have a concept of the instantaneous change in position, or instantaneous change in velocity, or any vector that you want. And so remember, previously we described the average velocity vector as the change in the position vector, or the displacement, divided by the change in time. But if we're not interested in, say, the average velocity over a long amount of time, but instead the exact velocity at a given point of time, we need to use something else, known as a derivative. And so you might wonder why we might care about the instantaneous velocity. And so again, going back to the idea of speed limits, well, you might drive for a very short burst of time at 100 miles an hour, and then the rest of the time drive at 20 miles an hour and say, oh, my average velocity was below the speed limit. But the police officer would say that he saw you driving instantaneously 100 miles an hour. So it'd be better to know what the derivative of the position is, or the instantaneous velocity. All right, so how do we get an idea of an instantaneous velocity, or a derivative? So we can use the concept of a tangent line. So if you have a given curve, say y equals f of x, shown in this plot as the black line, and you wanted to know what the slope of a line is that passes through a given point and on that line, and has only one contact point. So that would be this reddish line labeled t. So that is the tangent line, since it only intersects our curve at a single point. So say this point P is at x equals a, and our y value is f evaluated at a. And so it would have the slope given here, where the slope is equal to the limit as x approaches a of f of x minus f of a divided by x minus a, provided that that limit exists. So another way to write the slope of this special tangent line is by taking the limit as h goes to 0 of f of a plus h minus f of a over h. And so h is taken as a small change in your x value. So the slope of the tangent line evaluated at our given point x equals a is given as the derivative f prime of a equals the limit as h approaches 0 of this function f of a plus that small h minus f of a over h. Now, if we don't really care what this point a is, and we want to get the derivative as a function of x instead, so we have a new function that we can keep plugging x into, it would instead be f prime of x equals the same thing as before, but then changing our a for an x. Now, there are many different ways that you can see the derivative notation in the literature or when you're doing problems, and it really comes down to what's most convenient. Usually, the best way to write it is to have, say, df dx, this middle one over here, and that will become important when you're doing things like integration. But it's very common to see things such as f prime of x or y prime, as well as, sometimes this d f of x, or even d sub x of f of x. Anyway, and I'll also show you some more that are very common in vector notation, where you use little dot symbols above your vector in order to determine what order of a derivative it is. If it's the first order, it'd be a single dot, and then if you take the derivative again, it'd be two dots, and so on. But most of the time, I'll use either f prime of x or df dx. Okay, so now what are some common derivatives and some rules to keep in mind? So the first and most basic one is that if you have a function, say variable x raised to a power that's a constant a, and the constant can be either an integer or a decimal, whatever you want, Then, when you take the derivative, so d dx of x of a, you take that constant value in the exponent and you bring it down to multiply your original x, and then you reduce the power by 1 unit. So that one is very common to see, especially when you're working with polynomials, since you'll have a lot of things that have x to different powers. Okay, and so another set of very common derivatives are both your exponential functions and your logarithmic functions. So remember, on a previous lecture that I had, the exponential functions are anything with a base that's a constant value raised to a variable exponent. So if the base is e, or Euler's number, it'd be e to the x. And if it's any other base, say if the base is like 2 or 10, that can be called just a in general. And so a to the x. So what do exponential functions do? So with e to the x, when you take the derivative of that, you just get the original function, e to the x, which is quite convenient. It's a little bit different with a different type of base, like a being a greater than 0, since the derivative of a to the x would be a to the x, just like before, multiplied by the natural log of a. And recall, the natural log is just the inverse function of the e to the x exponential function. So, cool. And so, now that we remember, maybe, what logarithmic functions are, the derivative of a logarithmic function, such as the derivative of natural log of x, is just 1 over x. And this is just requires that x is greater than 0, just based on how the logarithmic function works. It's always greater than 0. And then logarithmic function of any base that you want, say base 10, 2, 1,000, would just be the derivative of that is log base a of x is 1 over x, and then times 1 over natural log of a, given that x and a are both greater than 0. And so you can see how there's a connection between both a different base and the exponential function. You multiply by natural log of a, and a different base in the logarithmic function, you get a multiplied by natural log of a. Cool. Now, very common trigonometric functions. So the derivative of a sine of x function gives you cosine of x. The derivative of a cosine function is negative sine of x, and the derivative of a tangent function is secant squared of x. The derivative of inverse functions are also very common to see. So like the derivative of arcsine would be 1 over the square root of the quantity 1 minus x squared, given that x is between -1 and 1. The derivative of arc cos x is equal to the negative of the derivative of arcsine of x. And then the derivative of arctangent of x is 1 over 1 plus x squared. All right, so now some common rules to keep in mind. So the derivative of a constant equals 0. So for example, if f of x just is a constant a, then the derivative of f of x just equals 0. And then if you have two functions added together, then their derivative is just the sum of their individual derivatives. So if you have f of x equals a constant a times g of x plus a constant b times h of x, then the derivative would just be the derivative of b times h prime of x plus the derivative of a times g prime of x. All right, and then the product rule. So if you have two functions that are multiplied by one another, then the derivative would just be the derivative of the first function times the original second function plus the derivative of the second function times the original first function. And so typically with both the sums and the products and even the quotient that will come up in a second, is you can identify on your own, given a very complicated function, what you could call f of x or g of x or h of x in order to always use the correct rule. Okay, but I guess one special type of product rule is that if one of the functions is equal to a constant, say if f of x is a constant a, we get a special case. So remember that the derivative of a constant just equals 0. So if you were to apply the product rule, say h of x equals a times g of x, then the derivative h prime of x would equal a prime times g of x plus a times g prime of x. Well, a prime just equals 0, so that first term goes away. So you end up with h prime of x equaling a times g prime of x. And so, yeah, so it's what we would expect. All right, so now the quotient rule. So if you have, two functions, one divided by the other, then the derivative would equal the derivative of that, rational function. And that would equal the lower function times the derivative of the upper function minus the upper function times the derivative of the lower function divided by the lower function squared. And then finally, the chain rule. So if you have a composite function, so say f of x equals h of g of x, then the derivative of f of x would equal h prime, so the outer function, its derivative, evaluated at the original function g of x, multiplied by the derivative of that interior function. Okay, so how do we use this to describe motion? So typically, our variable is, our independent variable is time, and our dependent variable takes the form of a vector. And this vector can be the position vector r that can have vector components in multiple coordinate directions. And so, first, I just wanted to say that when you take the derivative you can choose any of the coordinate directions, and these would be partial derivatives based upon, say, if you want to take a derivative with respect to the x direction, then you would take the derivative of the entire function with related to the x direction, leaving everything else as a constant. And so remember, the derivative of a constant just equals 0. So I'll get to that more later when I discuss more about calculus, but for now, most of the things that we'll worry about is just the derivative of the entire vector direction r, so along the direction of the position. And so if we were to do that, the derivative of position is your instantaneous velocity. Derivative, again, of the velocity would be your acceleration, and so on. Then you would have third derivative jerk, snap, crackle, and pop. And this is always when you take the total derivative in the direction of your position. And so now we have the formalism in order to determine the instantaneous velocity of a lot of various functions.